There is no road between the galaxies, no pavement, no painted line, no surface carrying one place toward another. Yet on the largest scales, we can observe matter does not gather at random. Galaxies collect in long chains. Clusters appear where those chains meet. Between them lie broad regions with far less matter, like open spaces left between the branches of an immense, unfinished pattern. Astronomers call this pattern the cosmic web. If every galaxy could be dimmed for a moment, the deeper arrangement would remain, an unseen landscape of mass, traced indirectly by motion, light, and gravity. It is made of knots, filaments, walls, and voids. The brightest parts are traced by galaxies, but most of the structure is not made of starlight. Dark matter supplies much of the gravitational framework, while ordinary matter, gas, stars, planets, and everything built from atoms tends to follow the same underlying arrangement. The web is not an object laid across the universe. It is the shape that matter has gradually taken under gravity. Its beginnings were almost featureless. In the early universe, matter was distributed with tiny differences from one region to another. Some places were only slightly denser than their surroundings. That small advantage was enough. A denser region exerted a little more gravitational pull, drawing in additional material, becoming denser still. Across billions of years, the faint irregularities deepened. Matter collapsed first into broad sheets, then into narrower filaments, and finally into crowded intersections where galaxy groups and clusters could grow. But the cosmic web is not merely a frozen map. Matter continues to move through it. Gas can fall away from the emptier regions and gather around filaments. Galaxies and smaller groups can travel along those filaments toward denser nodes. Near the intersections, gravity becomes stronger, temperatures rise, and the motion grows more complicated. Some gas may feed galaxies. Some may be heated by shocks. Some may remain spread thinly between systems, difficult to see even with instruments designed to search for it. Observations and simulations both support this broad picture, though many details of the flow remain active areas of research. The word highway is useful, but only if we hold it lightly. A cosmic filament has no hard edge. It does not carry traffic in a single direction. It can widen, twist, merge, and change as the universe expands and gravity reshapes the matter within it. A galaxy does not glide down its center like a car on a road. Its path is curved by many gravitational pulls at once, including nearby galaxies surrounding dark matter and the larger concentration waiting farther ahead. Even so, the image points towards something real. The universe has pathways. They are not designed and they are not still. They emerge from gravity acting on matter over distances so large that a single filament may extend for tens or hundreds of millions of light years. Along them, material is gathered, redirected, heated, stripped away, and sometimes delivered into places where new stars can form. Tonight, the journey will follow those motions. We will begin near the emptier spaces, where matter is sparse but not absent. From there, we will move toward the walls and filaments, enter the environments around galaxies, and continue toward the crowded nodes where clusters assemble. The scale will widen and narrow as needed, from the slow drift of intergalactic gas to the architecture of the observable universe. Nothing in this web needs to hurry. Its currents have been flowing for billions of years, and they are still carrying the universe into shape. Long before the first galaxy began to shine, the roots of the cosmic web were already being prepared. The early universe was hot enough that matter could not yet settle into stars, planets, or any of the structures familiar to us. Space was filled with a dense mixture of particles and radiation, all interacting so frequently that light could not travel far without being scattered. There were no clear beams crossing open distances. There were no dark gaps between luminous objects. There was only an expanding sea of energy and matter. cooling as space itself grew larger. This early state was remarkably even, but not perfectly even. Some regions contained a little more matter than others. Difference might be difficult to imagine because it was so small. It was not the difference between a crowded city and an empty desert. It was closer to a slight thickening in a nearly uniform mist. Yet, gravity responds to any difference in density. A region with a little more matter has a little more gravitational pull, and that pull can attract still more matter from nearby space. The process begins without spectacle. A slightly denser patch draws material inward. Its gravitational influence strengthens. Nearby, matter moves toward it more readily, increasing the density again. Over time, the original imbalance grows. What began as a faint variation becomes a foundation for larger structure. Dark matter was central to this growth. Unlike ordinary matter, dark matter does not interact with light in the usual way. It does not glow, absorb visible radiation, or form bright clouds that telescopes can photograph directly. Its presence is inferred from gravity, from the motion of stars within galaxies, from the behavior of galaxy clusters, from the bending of light, and from the way large structures form across cosmic time. In the young universe, ordinary matter was tightly coupled to radiation. Photons pushed against charged particles, resisting some of the collapse that gravity was trying to produce. Dark matter did not feel that same pressure from light. It could begin gathering into denser regions, while ordinary matter remained caught in the hot, restless mixture. This gave dark matter a head start. Its growing concentrations became gravitational wells. Later, as the universe cooled and ordinary matter separated from radiation, atoms could form and light could travel more freely. The universe became transparent. Gas then began falling more effectively into the structures that dark matter had already started to build. The oldest light we can observe preserves a record of those early differences. It comes from a time about 380,000 years after the beginning of cosmic expansion, when the universe had cooled enough for electrons and nuclei to combine into neutral atoms. The light released from constant scattering has traveled through expanding space ever since. Today we detect it as the cosmic microwave background. Across that background are tiny variations in temperature. A slightly warmer or cooler patch reflects subtle differences in the density and motion of the early material. These are not pictures of galaxies. They belong to a much earlier stage, before stars had formed. But within their pattern are the seeds from which galaxies, clusters, filaments, and voids would eventually emerge. The present-day cosmic web is therefore not disconnected from the early universe. It is the grown form of those first variations. Gravity amplified the differences. Expansion carried regions apart. Matter flowed toward denser areas and away from regions that gradually became emptier. The geometry that emerged was not a collection of isolated spheres. It developed into something more connected. When matter collapses under gravity, it does not always fall equally in every direction. A region may contract fastest along one axis, forming a broad sheet. That sheet may then collapse more strongly along another direction, producing a filament. Matter can continue to move along the filament toward a denser intersection, where a cluster or group of galaxies may assemble. This unequal collapse helps explain why the universe forms a web rather than a uniform field of separate clumps. The pattern contains hierarchy. Small structures form within larger ones. Galaxies develop inside dark matter halos. Groups of galaxies gather within broader concentrations. Clusters sit at major junctions. Filaments connect those junctions, while thinner strands branch away into less crowded regions. The boundaries are not sharp and the scales overlap. A structure that appears narrow from one perspective may contain countless smaller systems. The web also changes with time. In the distant past, it was less developed. the contrast between crowded and empty regions was lower. As billions of years passed, gravity continued drawing material toward the denser parts. Filaments became more pronounced. Nodes grew heavier. Voids lost more of their matter to the structures around them. Cosmic expansion continued throughout this process. Gravity pulled matter together locally, while expansion increased the distances between large regions of space. These two tendencies did not cancel one another everywhere. Inside bound systems, gravity could dominate. Across sufficiently large scales, expansion continued to widen the universe. The web formed within that balance. It did not resist expansion as a single connected object. It evolved while space expanded around and through it. Some regions became firmly bound. Others drifted farther apart. The result was a universe in which local gathering and large-scale separation could happen at the same time. There is no central location from which the web spread outward. Every part of the observable universe belongs to the same history of expansion and gravitational growth. From any galaxy, the larger pattern would extend in all directions, limited only by the distance light has had time to travel. Our own location lies inside this arrangement. The Milky Way belongs to a small group of galaxies. That group occupies a larger environment shaped by nearby filaments, galaxy concentrations, and broad, underdense regions. The night sky may appear to surround us with scattered points, but those points do not float independently. Each one belongs to a history of gathering that reaches far beyond the individual star. Even the atoms now resting within a human body entered this architecture long after it began. Hydrogen followed gravitational currents into early structures. Stars transformed some of that material into heavier elements. Galaxies exchanged gas through inflow, outflow, collision, and stripping. Across immense spans of time, matter moved from the early universe into the complicated systems that could eventually produce worlds. The cosmic web is not only the arrangement of distant galaxies, it is the deep history of where matter has been allowed to go. To understand the highways, it helps to begin with the spaces they leave behind. Cosmic voids are the broad underdense regions between the filaments and walls of the web. Some extend across tens of millions of light years. A few are larger still. They are not completely empty, but compared with the crowded regions around them, they contain far fewer galaxies and much less matter. Their emptiness is not accidental. As gravity drew material towards slightly denser places, the regions between those concentrations lost matter. Gas and dark matter moved outward, not because the voids were pushing them away, but because the surrounding structures were pulling more strongly. Over time, the difference grew. The filaments became richer, the voids became more rarefied. This creates one of the broadest movements in the universe. Matter tends to leave underdense regions and drift toward their boundaries. From those boundaries, it can move into sheets and filaments. Within the filaments, it may continue toward galaxy groups and clusters. The full motion is complicated, but its overall direction follows the gravitational landscape from lower density toward higher density. A void can therefore be understood as more than an empty place. It is part of the engine that shapes the web. Imagine a shallow basin spread across a floor, surrounded by deeper channels. A drop of water placed near the center may move only gradually, but over enough time it will find the lower roots. Cosmic matter follows gravity rather than a physical surface, yet the comparison offers a useful sense of direction. The void is the higher ground. The filament is the channel. The cluster is the deepest gathering place. The comparison also has limits. The cosmic web exists in 3 dimensions, and its gravitational terrain changes as matter moves. There is no fixed floor beneath it. The channels deepen while material enters them. The basin expands while it loses matter. Space itself stretches, carrying distant structures apart, even as local gravity draws nearby material together. Within a void, the remaining galaxies can appear isolated. They may be separated by distances greater than those typical in richer environments. Some are small and faint. Others continue forming stars from the gas available to them. Their surroundings are less crowded, but they are not cut off from the history of the universe. They still occupy dark matter halos. They still exchange energy and matter within their own systems. They still respond to the larger gravitational arrangement beyond the apparent emptiness. A galaxy inside a void does not need to know where the nearest cluster is. Gravity already contains that information. Every nearby concentration contributes to its motion, though some contributions are far stronger than others. The galaxy's path emerges from the sum of these pulls, combined with the expansion of space and the gravitational influence of its immediate environment. It may move toward a thin filament that is difficult to detect, or remain in a small local structure that has not yet joined a larger flow. The result is not a clean river of galaxies, leaving every void in neat lines. Some motions are slow. Some are interrupted by nearby companions. Some galaxies belong to small groups whose internal gravity dominates their local behavior. Yet, when astronomers examine sufficiently large populations, the directional pattern becomes visible. Matter drains away from the centers of voids and gathers around their edges. These edges are often where the first recognizable structures appear. A void may be surrounded by a wall, a broad flattened arrangement of galaxies and matter. Where walls intersect, they can form filaments. Where several filaments meet, the density rises again, producing the environments in which groups and clusters assemble. This gradual progression gives the web its layered character. Void, wall, filament, node. The categories are useful, but nature does not draw firm boundaries between them. A thin filament may pass through a void. A wall may curve rather than remain flat. A node may contain several clusters rather than one. The same region can look different depending on the scale at which it is mapped. From far enough away, a collection of galaxies may appear to form one continuous strand. Seen more closely, the strand separates into groups, smaller branches, and gaps. Within those groups are individual galaxies. Within each galaxy are stars, gas clouds, black holes, and planetary systems. The architecture repeats its pattern of gathering without reproducing the same structure at every level. The word empty also changes with scale. A region that appears nearly vacant in a map of bright galaxies may contain diffuse gas, dark matter, small galaxies, and particles too thinly spread to shine in any obvious way. Even the emptiest cosmic environment is crossed by light. Photons from distant sources move through it. Neutrinos pass almost without interaction. Expanding space continues to alter the distances between everything on either side. A void is not a hole in the universe. It is the universe in a more diluted state. Its low density changes how structures inside it evolve. With fewer neighboring galaxies, close encounters and mergers may happen less often. Gas may be less disturbed by the crowded conditions found in clusters. Small systems can develop with a different history from similar galaxies in denser regions. This makes void galaxies valuable to astronomers. They provide a way to study how environment influences growth. If two galaxies have similar masses but live in very different surroundings, their star formation, gas content, shape, and history may reveal how strongly the larger web has affected them. The comparison is rarely simple. A galaxy's present appearance records many influences at once. Its original dark matter halo, the gas it acquired, the stars it formed, the feedback from those stars, the behavior of its central black hole, and any interactions it experienced. Environment is one part of that record, but it can be a powerful one. The influence becomes clearer near a void's boundary. Here, Galaxies may align with sheets or filaments. Their motions begin to reflect the stronger pull of nearby structure. Gas that was once spread through a broad region becomes more concentrated. The web develops definition. This is where the idea of a hidden highway becomes easier to see. The highway does not begin as a bright lane. It begins as a preference in motion. A particle of dark matter follows the curvature created by surrounding mass. A cloud of gas responds to gravity while also feeling pressure and heat. A small galaxy moves with its local group. None of these objects is aware of a destination. Yet each trajectory is shaped by the same uneven distribution. Over millions and billions of years, those preferences become pathways. The largest paths can be inferred from the positions of galaxies, but position alone shows only part of the story. Astronomers also study motion. A galaxy participates in the overall expansion of the universe, but it can have an additional velocity caused by nearby gravity. This local deviation is called peculiar velocity. There is nothing peculiar about it in the ordinary sense. It is simply the motion left after the broad cosmic expansion is taken into account. These velocities help reveal where matter is flowing. Galaxies on opposite sides of an overdense region may move toward it. Galaxies near an expanding void may appear to stream away from its center. By combining many such measurements, researchers can reconstruct parts of the gravitational landscape that visible light alone cannot fully show. The work is difficult because distances are hard to measure precisely. A galaxy's light can tell us how rapidly it appears to recede, but separating expansion from local motion requires an independent estimate of distance. Small uncertainties can become large uncertainties in the inferred flow. For this reason, maps of cosmic motion are built patiently, using many galaxies and several methods. Even incomplete maps reveal a universe that is not sitting still. The galaxies around us are moving within local gravitational structures, while those structures occupy the greater web. Some motion is toward nearby concentrations. Some reflects the influence of broad under denser regions. Some belongs to the history of groups that formed long before their present paths could be observed. Our own galaxy shares in this movement. The Milky Way travels with the local group, accompanied by Andromeda, the Triangulum Galaxy, and many smaller systems. The group is gravitationally connected, yet it also lies within a large pattern of nearby matter. Its motion is influenced by concentrations beyond the group and by the uneven distribution of mass across the surrounding region. From the surface of Earth, none of this motion can be felt. The ground remains beneath you. The room holds its familiar shape. A nearby sound fades, and the night continues at the scale of ordinary life. At the same time, the Milky Way is participating in a flow that began before Earth existed. The atoms around you belong to a galaxy, moving through a network shaped by voids, filaments, and gravity. There is no wind from that motion, and no vibration announcing it. The scale is too large, and the movement is shared too completely. The voids remain out there, widening and thinning. Along their edges, the first faint roots gather definition, and matter begins to find the filaments. A filament is easiest to notice by what gathers along it. In a map containing thousands or millions of galaxies, a filament appears as an elongated concentration, a bridge of structure extending between denser regions. It may connect galaxy groups, led toward a cluster, or branch into several thinner strands. The galaxies make the route visible, but they are only the bright markers. Most of the mass shaping the filament does not shine. Dark matter provides much of its gravitational backbone. This does not mean that dark matter forms a narrow cable with ordinary matter wrapped around it. A cosmic filament has a broad and uneven cross-section. Its density rises gradually from the surrounding space, and smaller halos, gas clouds, and galaxies are embedded throughout it. Some parts are thick and crowded, Others are faint enough that their existence can be inferred only by combining many observations or comparing them with simulations. Gravity has drawn both dark matter and ordinary matter into the same large-scale pattern, but the two do not behave in exactly the same way. Dark matter responds mainly to gravity. Gas also responds to pressure, temperature, radiation, magnetic fields, and violent events inside galaxies. When streams of gas approach a filament, they may be compressed. Their motion can become disordered. Shocks can convert part of their inward movement into heat. Material that began cold by cosmic standards may be warmed to hundreds of thousands or millions of degrees. This diffuse, heated material is often described as the warm-hot intergalactic medium. The name covers a wide range of conditions rather than one uniform substance. The gas is extremely thin. Even when its temperature is high, its density can be so low that it produces only a faint signal. A person placed there would not experience anything like a hot atmosphere. There would be too few particles arriving at once. Temperature describes the average energy of individual particles, while density tells us how many of those particles occupy a volume. In the cosmic web, high particle energy and very low density can exist together. Much of this gas is ordinary matter, made mostly of hydrogen and helium. For a long time, astronomers faced an accounting problem. Measurements of the early universe indicated how much ordinary matter should exist. Yet surveys of stars, galaxies, and readily visible gas found less than expected in the nearby universe. The matter was not thought to have vanished. It had become difficult to detect. Cosmic filaments offered a likely hiding place. As structure formed, gas outside galaxies was drawn into the web and heated. Some remained too cool and diffuse for strong X-ray emission. Some became too hot to show the signatures used for colder hydrogen. Spread across enormous volumes, it could contain a substantial amount of matter while remaining nearly invisible. In any single observation, finding it required new ways of looking. One method uses a bright object much farther away. A quasar can serve as a background lamp, sending light through intervening space before that light reaches a telescope. If the beam crosses diffuse gas, atoms and ions remove particular wavelengths. The resulting absorption lines act like fingerprints. They can reveal the presence, motion, temperature, and composition of material that emits almost no detectable light of its own. The filament is not photographed as a glowing rope. It is read from what it does to light passing through it. Another method searches for faint X-rays from very hot gas, especially where a filament approaches a massive cluster. There, infalling material can be compressed and shock heated more strongly. The signal is still difficult to separate from galaxies, active black holes, forts, foreground material, and the bright gas already filling the cluster. Long observations and careful modeling are needed to determine which emission belongs to the bridge itself. Gravity offers a different route. A concentration of mass bends the path of light from more distant galaxies. The distortion is small, but when many background galaxies are measured together, their shapes can reveal a pattern of weak gravitational lensing. This allows astronomers to map mass, whether or not the mass emits light. In several systems, lensing has exposed bridges of matter between neighboring clusters, providing direct evidence for the dark framework of a filament. Each technique detects a different part of the same structure. Galaxy surveys trace the luminous population. Absorption spectroscopy samples thin columns of gas. X-ray observations favor hotter regions. Gravitational lensing responds to total mass. Radio and microwave measurements can add information about ionized material and pressure. No single method delivers a complete portrait. The cosmic highway must be assembled from overlapping clues. This is one reason computer simulations are so important. A simulation begins with a model of the early universe. and follows the growth of structure under gravity, expansion, and the physics of gas. Researchers can then compare the simulated distribution of galaxies, dark matter, and intergalactic material with observations. The comparisons is not a decorative exercise. If a model produces filaments that are too thick, clusters that grow too early, galaxies with the wrong properties, or gas at the wrong temperatures, then some part of the physical description needs attention. The web connects cosmology with galaxy formation. It allows theories about the universe as a whole to be tested against the environments in which individual galaxies live. Within a filament, matter does not move as one continuous stream. Dark matter particles cross and recross one another through the gravitational structure. Gas can collide, heat, cool, and change direction. Galaxies carry their own dark matter halos and may belong to small groups whose internal gravity shapes their immediate paths. Outflows from stars and central black holes can push enriched gas away from galaxies and into the surrounding filament. The result is a mixture of inward supply and outward return. Pristine or lightly enriched gas can move toward galaxies from the intergalactic medium. At the same time, galaxies release material processed by stars. Heavy elements such as carbon, oxygen, silicon, and iron can be carried beyond the visible disks where they formed. Later, some of that material may cool and fall back, or mix with gas moving through the larger web. A filament is therefore not only a road toward a cluster, it is also a reservoir, a boundary, and a record of exchange. Near its outer regions, matter may still be arriving from sheets and voids. Farther inward, gas and galaxies may be directed along the filament's length. Around embedded halos, material can turn toward individual galaxies. Near a cluster, the flow becomes more turbulent as several streams converge. The direction depends on scale. A parcel of gas may be moving toward the center of a filament, while the filament as a whole feeds a cluster. A galaxy may be falling into a group, while that group travels toward a denser node. These nested motions make the highway image more accurate than it first appears, provided the road is imagined as something with depth, branching lanes, changing currents, and no fixed surface. There may also be a subtle rotation in some filaments. Studies of galaxy motions have reported patterns consistent with matter turning around a filament's long axis. The interpretation remains an active subject because measuring such motion across immense distances is difficult, and different structures need not behave identically. Simulations do show that angular momentum can emerge as matter falls unevenly into the web. Nothing had to set the filament spinning from outside. Gravity acting on an irregular distribution can create torque. Material approaching from different directions carries different momentum. As streams merge, some of their motion can become rotation. The same broad principle appears elsewhere in astronomy. From the spin of galaxies to the disks around young stars, though the scales and details differ, filaments can influence the orientation of the galaxies within them as well. In simulations and surveys, galaxy spins and shapes show statistical relationships with the surrounding web. Lower mass and higher mass galaxies may respond differently, partly because they have different merger histories and ways of acquiring matter. These are population trends, not rules for every object. A single galaxy may have been turned, disturbed, or rebuilt by local events. Still, the larger environment leaves traces. A galaxy does not grow in isolation and then happen to enter the web. Its supply of gas, its encounters, its angular momentum, and its eventual destination are connected to the structure around it from an early stage. The filament is part of the conditions under which the galaxy becomes what it is. For generations, astronomers first mapped the bright points. They measured positions on photographic plates, then gathered spectra, redshifts, and digital images across wider fields. Gradually, flat sky maps became three-dimensional surveys. What had looked like scattered islands began to reveal walls, chains, and spaces between them. Later instruments turned toward the material between the islands. A faint absorption line in a quasar spectrum, a slight distortion in the shape of a background galaxy, or a weak band of X-rays, could now be placed within the larger pattern. Separate observations, sometimes collected years apart and by different teams, became parts of one structure. The web emerged through accumulated attention. Even now, much of a filament remains beyond direct view. Its boundaries depend on how they are defined. Its gas changes temperature from place to place. Its dark matter can be mapped only through gravitational effects, yet its influence appears repeatedly in the positions of galaxies, in the heating of gas, and in the growth of clusters. The highway is hidden, but its traffic leaves evidence. And farther along the filament, where several routes begin to converge, the galaxies themselves start to change. A galaxy does not arrive at a cluster unchanged. Long before it reaches the crowded center, the surrounding web has already begun to shape it. The filament guides its motion, but it also changes the conditions through which the galaxy travels. The density of nearby matter rises. Encounters become more likely. Gas outside the galaxy becomes warmer and more pressurized. Small groups gather along the route, carrying several galaxies together toward the same destination. This gradual transformation is sometimes called pre-processing. The word describes changes that occur before a galaxy enters a major cluster. A galaxy may first fall into a modest group, interact with companions, lose part of its gas, or experience a burst of star formation. By the time the larger cluster captures it, much of its earlier evolution has already taken place along the way. A filament is therefore more than a channel of delivery. It is an environment in its own right. Near the less crowded sections, a galaxy may still receive gas from the surrounding medium. That gas can descend into its dark matter halo, cool, and eventually join the rotating disk. Once dense enough, parts of it may collapse into molecular clouds, allowing new stars to form. This supply is not constant. The rate depends on the galaxy's mass, the temperature of the surrounding gas, the strength of stellar and black hole feedback, and the structure of the filament itself. Some galaxies continue to draw material inward for long periods. Others find that the available gas has been heated too strongly to cool efficiently. A galaxy can appear self-contained from a distance, but its life depends on this exchange. Stars consume cold gas. Massive stars return part of their material through winds and explosions. Central black holes can release energy into the surrounding halo. Without some form of replenishment, the galaxy's reservoir gradually declines. New stars become less frequent, and the light of the remaining stellar population slowly changes. The cosmic web helps determine whether replenishment continues. In thinner environments, cool gas may reach a galaxy with less interference. Near larger groups and clusters, incoming gas encounters hotter and denser material. The stream can be disrupted, mixed, or prevented from reaching the central disk. The galaxy may still contain enough fuel to form stars for a time, but the connection to its larger reservoir has weakened. This process is often described as starvation or strangulation. Neither term implies a sudden event. The supply is reduced rather than instantly removed. The galaxy continues using the gas it already has. Star formation fades over hundreds of millions or billions of years, depending on the system. From the outside, the change can appear gradual, a slow shift from a blue, actively star-forming galaxy toward a redder population dominated by older stars. Other changes can be more immediate. As a galaxy moves through surrounding gas, it experiences pressure. The stars and dark matter pass through with little direct resistance, but the galaxy's own gas collides with the external medium. If the motion is fast enough and the surrounding gas is dense enough, part of the internal gas can be pushed backward and stripped away. This is ram pressure stripping. The effect becomes especially strong inside massive clusters, where galaxies can move at high speeds through hot intra-cluster gas. Yet the early stages may begin in groups or near the denser portions of filaments. Extended reservoirs around a galaxy are easier to disturb than the tightly bound gas near its center. A galaxy can begin losing its outer supply before its bright stellar disk shows obvious damage. Sometimes the stripped gas forms a tail. Such galaxies can resemble luminous creatures moving through deep water with streams of gas trailing behind them. New stars may briefly form within the compressed material, creating bright knots along the wake. The image can look dramatic, but the physics is patient. The tail records the interaction between a moving galaxy and the medium through which it travels. Gravity also acts through encounters. Two galaxies passing near one another pull on each other's stars, gas, and dark matter. If the approach is close, their shapes can be distorted. Spiral arms may stretch, gas can be driven inward, star formation may increase for a time. If the galaxies lose enough orbital energy, they may eventually merge. In a rich cluster, galaxies often move so quickly that many close encounters are brief. They disturb one another without necessarily combining. In a smaller group, relative speeds are lower, making mergers more likely. This is one reason pre-processing matters. A galaxy group moving along a filament can transform its members before the entire group enters a larger cluster. The group travels as a small community within a much larger flow. Its galaxies share a common dark matter halo. They orbit, interact, and exchange material. Some merge into a larger central galaxy. Others remain as satellites. Gas can be removed from the smaller systems and added to the surrounding group medium. The group's history becomes part of the cluster's history when the two structures finally join. Clusters grow in this way. They do not collect galaxies one by one from a perfectly even background. They acquire groups, filaments, gas streams, and smaller concentrations of dark matter. Their outskirts are shaped by repeated arrivals from preferred directions. This can leave visible patterns. Galaxies may enter a cluster along the same filament. Subgroups may retain traces of their shared motion. The cluster can contain regions that have not fully mixed, even when its overall appearance seems settled. Astronomers study the velocities, temperatures, and positions of galaxies and gas to reconstruct these arrivals. A cluster is not simply the end of the highway. It is an intersection still being built. Matter enters from several directions. Some of it falls toward the center, some passes through and returns on a wider orbit. Dark matter halos overlap, gas streams collide and heat. Galaxies move through a gravitational field that changes as the cluster grows. The path of a single galaxy can be complicated. On its first approach, it accelerates toward the cluster. It may pass near the center, where tidal forces and ram pressure are strongest. If it remains gravitationally bound, it travels outward again, though usually not as far as before. Over repeated orbits, its path may shrink and its internal gas supply may diminish. Not every galaxy reaches the core. Some remain in the outskirts. Some are scattered onto wide trajectories. Some pass through the cluster environment once and continue outward, carrying the marks of that encounter with them. A galaxy found beyond the cluster boundary may already have crossed the dense interior in the past. The web does not sort galaxies into simple categories. History matters. Two galaxies at the same present distance from a cluster may have traveled very different paths. One may be approaching for the first time. The other may have passed through long ago. Their gas, star formation, and shapes may record those differences even when their current positions look similar. This is why astronomers combine many kinds of evidence. A galaxy's color gives clues about its stellar population. Spectral lines reveal ongoing star formation and gas conditions. Its shape may show tidal disturbance. Radio observations can map neutral hydrogen. X-ray measurements can reveal hot gas. Its motion relative to the cluster helps estimate where it may be in its orbit. No single clue tells the whole story. Together, they show that environment acts through several processes at once. A galaxy can lose its outer gas through pressure, have its remaining disk disturbed by a companion, and receive a brief inflow toward its center. Star formation may rise before it falls. A central black hole may become active. The stellar disk may survive even after the gas supply has changed. Transformation is rarely a clean sequence. It is a layering of effects. The larger cosmic web sets the route. The group environment shapes the first encounters. The cluster increases the pressure and speed. The galaxy's own mass and structure determine how strongly it responds. A massive galaxy can hold its gas more tightly than a smaller one. A compact system may resist stripping better than a diffuse disk. A galaxy entering phase, first through surrounding gas, may experience a different pressure pattern from one moving edge on. The same environment does not produce the same result in every case. Even within a single galaxy, different parts respond differently. The outer gas disk is more weakly bound and can be removed first. The inner gas may remain long enough to continue forming stars. Over time, star formation becomes concentrated toward the center before fading more broadly. The stellar disk, less affected by direct pressure, can remain visible after much of the gas has gone. This creates galaxies that carry their histories in layers. The old stars remember earlier periods of growth. The remaining gas records recent disturbance. The surrounding halo reflects the long influence of gravity. The galaxy's orbit ties all of these to the web beyond it. From Earth, such histories are reconstructed from light that began its journey at different times. Galaxy hundreds of millions of light years away is seen as it was hundreds of millions of years ago. Another, farther behind it, is seen at an earlier stage of cosmic history. By observing large populations across distance, astronomers can compare the web at different ages. The result is not a moving film of one galaxy. It is a collection of many systems, each captured at one moment, arranged into a broader account of change. There is something familiar in that patient method. Human understanding of the sky has always depended on fragments. One observer records a position, another measures a spectrum decades later. A new telescope finds faint gas that earlier instruments could not see. Across generations, separate pieces become a map no single lifetime could have completed. The same is true of the galaxies themselves. No one watches a galaxy travel from a thin filament into a cluster over billions of years. The movement is far too long. Instead, different galaxies reveal different portions of the route. One is still receiving gas, another is entering a group, another has begun to lose its outer reservoir, another circles inside a cluster, with little star formation remaining. Together, they trace the journey. For the listener resting now, the scale does not need to be solved all at once. It is enough to notice the continuity. Matter leaves the voids. It gathers in walls, it enters filaments. Galaxies grow within those filaments and begin to change as the environment becomes denser. Groups form along the route. Clusters wait at the intersections, not as final destinations, but as deeper stages in the same gravitational flow. And beyond the galaxies, another traveler is moving through the web. Gas, far more diffuse than any star system, continues toward the nodes, carrying heat, pressure, and the raw material from which future structure may still be made. At the densest intersections of the web, the highways lose their separate identities. Several filaments may approach from different directions, each carrying galaxies, dark matter, and diffuse gas. Their flows overlap inside a deeper gravitational basin. Groups arrive with their own histories, Smaller halos are absorbed into larger ones. Gas that traveled through relatively narrow channels enters an environment crowded with motion. This is where galaxy clusters grow. A cluster may contain hundreds or thousands of galaxies, but the galaxies provide only a small portion of its total mass. Most of the mass is dark matter, distributed through a halo much larger than the bright region visible in an ordinary image. Much of the ordinary matter lies between the galaxies as a thin plasma called the intracluster medium. Heated to millions of degrees, it fills the cluster with X-ray emitting gas. The cluster is not a dense crowd in the everyday sense. Distances between its galaxies remain enormous. A traveler crossing the cluster would spend most of the journey in open intergalactic space, yet compared with a void or a thin filament, the concentration is high, the gravitational field is deep, the gas is hot, and galaxies move rapidly on long orbits around the common center of mass. The heat of the intracluster medium is largely a record of falling. As gas descends into the cluster's gravitational well, it accelerates. Streams meet other streams. Groups collide with the existing cluster atmosphere. Shock waves and turbulence convert organized motion into random particle motion, raising the gas temperature. Gravitational energy becomes heat. The transition can begin far beyond the bright central region. Gas approaching from a filament may encounter an accretion shock near the cluster outskirts. The exact boundary is broad and uneven, changing with direction. Because matter does not arrive equally from all sides, along a major filament, dense material may penetrate farther inward. Between filaments, the surrounding gas may be thinner, and the shock structure different. There is no single spherical gate. The cluster's edge is a changing interface between the web and the node. Here, incoming gas is compressed. Electrons and atomic nuclei move more energetically. Magnetic fields can be stretched and rearranged. Some particles may be accelerated to much higher energies at shocks, producing faint radio emission under suitable conditions. These outer regions are difficult to observe, and the details of their particle physics remain under study. But simulations and observations increasingly reveal that cluster growth is written into the gas around the boundary. Farther inward, the intracluster medium becomes brighter in X-rays. It is still extremely diffuse by terrestrial standards. The particles are separated by distances much greater than those inside air, water, or solid matter. Yet the cluster contains so much volume that the total mass of this thin gas can exceed the mass locked inside all of its stars. The gas carries more than heat. It contains heavier elements forged inside earlier generations of stars. Oxygen, silicon, sulfur, iron, and other nuclei were released through stellar winds, supernova explosions, and outflows driven by active galactic nuclei. Some were stripped from galaxies as they crossed the cluster environment, mixed into the intracluster medium. These elements preserve a chemical history extending back through many episodes of star formation. The space between galaxies is not untouched material. It has been processed, expelled, stirred, and redistributed. An X-ray spectrum can reveal this history. Particular ions leave recognizable features in the cluster's emission. Their strengths help astronomers estimate the abundance of different elements. The measurements do not identify every star that contributed, but they show that material created inside galaxies has traveled far beyond them. A cluster can be thought of as a reservoir of shared matter. Galaxies enter carrying gas enriched by their own stars. Pressure and gravity remove some of it. Black holes and supernovae send additional material outward. The intracluster medium receives these contributions and mixes them across distances far larger than any individual galaxy. The mixing is incomplete. Some regions retain distinct temperatures or compositions. A recently arrived group may carry cooler gas into the cluster. A merger can produce arcs of compressed material and long disturbances in the X-ray atmosphere. Dense cores may survive for a time as they pass through one another, leaving wakes behind them. These patterns allow astronomers to reconstruct events that unfolded over hundreds of millions of years. A sharp edge in X-ray brightness may mark a moving front. A broad region of hotter gas may indicate a shock. An offset between visible galaxies, hot plasma, and gravitationally mapped mass may reveal how different components responded during a collision. Galaxies and dark matter can pass through one another with relatively little direct interaction. Gas cannot. It collides, slows, and heats. During a cluster merger, this difference can separate the glowing plasma from the dominant dark matter distribution. Gravity remains the common guide, but matter does not all travel in the same way. The cluster itself may take billions of years to settle after a major merger. Even then, smaller groups continue to arrive. Filaments continue feeding the outskirts. A node that appears mature is still participating in the growth of the web. Near the center, another exchange becomes important. The hot gas radiates energy. In some clusters, the central gas can lose heat more rapidly than gas farther out. As it cools, it should become denser and move inward. Early models suggested that this might produce large flows of cooling material and extensive star formation in the central galaxy. Observations found a more restrained outcome. Some gas does cool, and cold clouds and young stars can appear near cluster centers. But the amount is often smaller than a simple cooling model predicts. Something returns energy to the gas and prevents much of it from cooling freely. A central supermassive black hole provides part of the answer. When gas reaches the black hole's surroundings, a small fraction can release immense energy. Jets launched from the central region push into the intracluster medium. They inflate cavities, drive waves, and stir the plasma. The black hole does not need to heat every particle directly. By disturbing the surrounding gas, it can distribute energy across the cluster core. The process forms a feedback cycle. Cooling gas moves inward. Some of it helps feed the central black hole. The active black hole releases energy. That energy slows further cooling. As the activity declines, cooling can gradually resume. The balance is imperfect and its details differ among clusters. Yet it shows that the node is not shaped by gravity alone. On the largest scale, matter falls inward because of the cluster's mass. Near the center, energy from a region smaller than the solar system can influence gas spread across hundreds of thousands of light years. The scales meet inside the same structure. A filament delivers matter to the cluster. The cluster channels some gas toward its core. The black hole redirects part of the infalling energy outward. Jets, bubbles, turbulence, and cooling clouds become local movements nested inside the greater flow of the cosmic web. The node receives, transforms, and returns. Astronomers can study the hot gas through X-rays, but there is another way to detect it. Light from the cosmic microwave background passes through galaxy clusters on its journey toward Earth. As those ancient photons cross the hot intracluster plasma, some interact with energetic electrons and gain a small amount of energy. This change, known as the thermal Sunyaev-Zeldovich effect, allows clusters to be found through the imprint they leave on the background light. The signal has a useful property. Its surface brightness does not fade with distance, in the same way ordinary emitted light does. A distant cluster can therefore leave a detectable mark even when its galaxies and X-ray gas are faint. Surveys using this effect have discovered clusters across large spans of cosmic history and helped trace how massive structures accumulated over time. Once again, the cluster is known through an alteration in traveling light. Background galaxies are distorted by gravitational lensing. Microwave photons are shifted by hot electrons. X-rays emerge from the plasma. Visible and infrared light reveal the galaxies. Radio observations trace particles and magnetic fields. Each form of light encounters a different part of the node. Together, they reveal a structure that no single image contains. A photograph may emphasize the galaxies because stars are bright and familiar. A mass map shows the broader dark matter halo. An X-ray image fills the apparent emptiness with luminous gas. A microwave map records pressure. Spectra add motion, temperature, and composition. The cluster changes depending on which messenger is allowed to speak. This layered method has taken generations to build. The first observers recorded concentrations of faint objects in the sky without knowing their distances. Later, astronomers recognized those objects as galaxies gathered far beyond the Milky Way. X-ray telescopes revealed that the space between them was filled with hot plasma. Gravitational lensing exposed mass that could not be seen. Microwave surveys began finding clusters by the pressure of their gas. No observer needed to complete the entire picture. Each instrument added another physical layer, and the node gradually became visible as part of a much larger system. A galaxy cluster is sometimes described as one of the largest gravitationally bound structures in the universe. The description is useful, but it can make the cluster sound detached, like an island with a fixed shoreline. It is better understood as a place where the web gathers deeply enough to hold itself together. Its galaxies arrived along filaments. Its hot atmosphere was built through infall and collision. Its dark matter halo grew through the merging of smaller halos. Its heavier elements came from stars that lived and died inside countless galaxies. Its central black hole continues to exchange energy with the surrounding gas. The cluster is a meeting place of histories. Some matter crossed a void before joining a filament. Some formed stars in a small galaxy, was expelled and later mixed into the cluster atmosphere. Some dark matter entered inside a group that has since lost its separate identity. Some gas is arriving now, crossing the outskirts for the first time. And the arrival does not end at the node. Clusters tug on nearby structures, merge with other clusters, and remain connected to filaments that extend beyond their bound region. The highway continues through the intersection, carrying the pattern toward even larger scales. Beyond the individual clusters, the web becomes difficult to hold in a single view. A cluster may sit where several filaments meet, yet those filaments continue beyond it, linking one dense region to another across distances that can exceed 100 million light-years. Groups, clusters, walls, and empty regions become parts of broader patterns. From this scale, the universe no longer resembles a collection of separate objects. It begins to look like one connected distribution of matter. No telescope can step outside the universe and photograph that distribution from above. The map must be built from within. Astronomers begin with positions on the sky. A galaxy appears in a particular direction, but that direction alone gives only 2 dimensions. To locate the galaxy in depth, they measure its redshift, the stretching of its light toward longer wavelengths. Much of that stretching comes from cosmic expansion. In general, a more distant galaxy is carried away more rapidly as the space between us grows. By measuring redshift and applying a model of expansion, astronomers can estimate where the galaxy lies along the line of sight. Repeating the process for millions of galaxies produces a 3-dimensional survey. The first large maps changed the visual language of cosmology. Galaxies did not fill space evenly. They appeared in long arcs, narrow chains, crowded knots, and broad gaps. Some early survey slices looked almost biological, like foam or branching tissue seen through a microscope. The resemblance was only visual, but the pattern was unmistakable. The large-scale universe had structure. Modern surveys extend across wider areas and reach much farther into the past. Each galaxy in such a map is also a clock. Because light takes time to travel, distant regions are seen at earlier stages of cosmic history. A galaxy 1 billion light-years away appears as it was 1 billion years ago. A survey that reaches several billion light-years does not map one universal moment. It gathers many different ages into a layered view. Astronomers must account for this carefully. The nearby web is seen late in its development. More distant portions are seen when the filaments were younger, clusters were less massive, and galaxies often form stars more actively. By comparing different distances, researchers can study how the network grew. The map is not perfectly sharp. A galaxy's redshift includes more than the expansion of space. Local gravity gives the galaxy an additional motion. Inside a cluster, galaxies orbit in many directions at high speeds. When their redshifts are converted directly into distance, the cluster can appear stretched along the line of sight, forming a long false extension. This distortion has a useful name, the finger of God effect. The phrase sounds dramatic, but it describes a measurement pattern. A compact cluster becomes elongated in redshift space because its galaxies have different local velocities. On larger scales, coherent infall toward a dense region can produce a different distortion, compressing patterns in one direction. These effects complicate the map, yet they also contain information. The distortions reveal how galaxies are moving under gravity. They allow astronomers to test how rapidly structure grows and how matter is distributed. A problem in one kind of measurement becomes evident in another. Visible galaxies remain only traces. They shine where stars have formed, but the dark matter framework extends around and between them. To map that hidden mass more directly, astronomers turn again to gravitational lensing. Light from a distant galaxy does not travel through perfectly empty geometry. Matter along its path bends space and alters the route. A single foreground mass may create a noticeable arc or multiple image. Across the wider web, the distortions are usually much smaller. Each background galaxy is stretched by an amount that can be difficult to distinguish from its natural shape. One galaxy tells very little. Millions of galaxies tell more. By measuring their orientation statistically, astronomers can reconstruct the weak lensing field across a large region of sky. The result is a projected map of matter, including both visible and dark components. Dense regions produce stronger patterns. Filaments and smaller concentrations appear more faintly. This method does not require the matter to glow. It requires only that gravity bend the light passing near it. Another map comes from hydrogen. In the distant universe, bright quasars send their light through long stretches of intergalactic space. Along the way, the light passes through many separate clouds and filaments containing neutral hydrogen. Each region absorbs a narrow portion of the quasar's spectrum, shifted according to its distance. The spectrum becomes a forest of absorption lines. This is the Lyman alpha forest, one of the richest records of diffuse matter across cosmic history. Each line marks hydrogen along the path. With many quasars spread across the sky, astronomers can combine these separate sightlines and infer the three-dimensional distribution of gas between galaxies. The technique is like exploring a fog with many narrow beams. A single beam reveals only what lies directly along it. Thousands of beams begin to show the larger shape. The hydrogen does not always sit inside bright galaxies. Much of it occupies the lower density regions of the web, making the Lyman alpha forest especially valuable for studying material that would otherwise remain unseen. It extends the map beyond the luminous points and into the spaces between them. Radio astronomy offers another possibility. Neutral hydrogen can emit radiation with a characteristic wavelength of 21 centimeters. Individual distant galaxies may be too faint for easy detection, but large experiments can measure the combined emission from many unresolved systems. This approach, called intensity mapping, aims to trace broad structure without identifying every galaxy separately. Instead of cataloging each light, It measures the glow of the landscape. Different methods overlap in useful ways. Galaxy surveys reveal where luminous systems gather. Weak lensing maps total mass. Hydrogen absorption traces diffuse gas. X-rays reveal hotter regions. Microwave observations show the pressure of ionized material. Radio measurements can follow neutral hydrogen and magnetic activity. Each map has blind spots. A galaxy survey may miss faint systems. Lensing measurements are affected by the uncertain shapes and distances of background galaxies. Quasar sight lines are sparse. X-ray emission favors hotter and denser gas. Radio signals can be buried beneath brighter foreground radiation. The web is too broad and varied for one instrument to describe completely. Its portrait becomes clearer when independent methods agree. Computer simulations provide the bridge between them. A simulated universe can track dark matter, gas, stars, and black holes across cosmic time. Researchers can create artificial observations from the simulation, then apply the same limitations that affect real telescopes. Galaxies can be selected by brightness. Spectra can be blurred. Noise can be added. The simulated web can then be compared with the observed one on equal terms. This helps separate physical disagreement from observational bias. If the real universe contains fewer small galaxies than a model predicts, the difference might come from how stars form, how feedback removes gas, or how the survey detects faint objects. If lensing maps show a different growth rate from the model, the cause may involve cosmology, measurement uncertainty, or the way matter is represented. The comparison requires patience. Large-scale structure is shaped by several ingredients at once. The amount of dark matter, the behavior of ordinary matter, the initial density pattern, the expansion history, and the properties of dark energy. Changing one ingredient can alter the thickness of filaments, the abundance of clusters, and the growth of voids. This makes the cosmic web a test of the universe itself. Its arrangement preserves information from the earliest fluctuations. Its later growth records the influence of gravity. Its present scale reflects billions of years of expansion. The distribution of galaxies is not only a map of where matter happens to be, it is evidence of how the cosmos has behaved. Within that distribution is a subtle preferred scale. In the young universe, ordinary matter and radiation supported waves of pressure. These waves traveled outward from early overdense region before the universe cooled enough for atoms to form. When the radiation decoupled, the waves left a slight statistical imprint in the spacing of matter. Today, that imprint appears as a small excess in the probability of finding galaxies separated by a particular enormous distance. No observer sees a single ring drawn around one galaxy. The pattern emerges only when many galaxy pairs are counted. This feature, known as baryon acoustic oscillation, acts as a cosmic measuring tool. Its original scale can be calculated from early universe physics. Comparing that known scale with its apparent size at different distances helps astronomers trace the history of expansion. The web becomes a ruler. Its galaxies mark the measurement points, while the ancient pressure waves provide the reference length. Through this method, a pattern established for the first stars can be used to study the universe. Billions of years later, there is a long generational thread in such a map. The light is collected by instruments built from the work of many earlier observers. Survey teams may include hundreds of people. Some design detectors, some calibrate spectra, some develop software. Others compare the results with models that took years to compute. No one person sees the whole web directly. The structure appears through shared methods, repeated measurements, and careful agreement between different forms of evidence. A map published today may depend on starlight that began traveling before Earth had complex life, on equations developed generations ago, and on machines assembled by people who will never visit the places they reveal. The cosmic highways are mapped by cooperation across time, and when those maps are placed beside one another, the universe begins to show not only where matter has gathered, but how the entire network is still changing. The cosmic web is still growing, but not everywhere in the same way. Gravity continues to pull matter toward dense regions. Galaxy groups merge, clusters gain mass, filaments guide material toward their intersections. Inside these bound structures, motion remains active, and the architecture can continue changing for billions of years. Across much larger distances, another influence becomes more important. The expansion of the universe is accelerating. The name given to the unknown cause is dark energy. The term does not identify a substance that has been directly collected or examined. It describes whatever is responsible for the observed acceleration in cosmic expansion. Its physical nature remains one of the largest open questions in cosmology. The evidence appears through several independent observations. Very distant stellar explosions reveal how the expansion rate has changed over time. Measurements of the cosmic microwave background establish conditions in the early universe. Galaxy surveys and the large-scale pattern of matter show how structure developed afterward. Together, these observations support a universe in which ordinary matter, dark matter, and a dominant dark energy component influence the cosmic history in different ways. Dark matter helps structure grow. Its gravity deepens the wells into which gas and galaxies fall. Dark energy acts differently. On sufficiently large scales, accelerated expansion increases the separation between regions that are not gravitationally bound. It does not pull galaxies out of a stable cluster one by one. It changes the wider background in which clusters and filaments exist. This distinction matters. Inside the local group, gravity is strong enough to dominate over expansion. The Milky Way and Andromeda are approaching each other. Their future interaction will unfold according to their shared gravitational field, along with the influence of the smaller galaxies and dark matter surrounding them. Between much more distant galaxy groups, expansion can dominate. As time passes, some regions move beyond one another's ability to exchange new signals. Their light becomes increasingly stretched. The structures remain part of the same cosmic history, but their future contact grows more limited. The web therefore develops unevenly. Bound knots can continue merging internally, while the distances between separate bound regions grow. Some filaments may keep feeding nearby clusters for a long time. Others may be stretched across expanding space, their matter becoming too dispersed to assemble into new large structures. The great network will not disappear in one event. Its future is a gradual separation. This helps explain why the cosmic web is most active during a particular era. In the very early universe, the density differences were small, and the network had only begun to emerge. Later, gravity produced galaxies, filaments, and clusters with increasing contrast. In the far future, accelerated expansion is expected to slow the growth of structure on the largest scales. The universe has not always looked equally web-like, nor will it continue changing at the same rate forever. This is one reason observations at different distances are so valuable. Looking farther away means looking further into the past. A deep survey does not merely expand the map. It allows astronomers to compare the network at several stages of development. The younger web appears less settled. Clusters are smaller. Some filaments are still assembling. Galaxies contain more gas and often form stars more rapidly. Major mergers are more common. The structure is present, but its knots have not yet accumulated the mass they will hold later. Closer to our own time, the broad pattern is more mature. Voids are larger and emptier. Many clusters have gained substantial hot atmospheres. Numerous galaxies have reduced their star formation, especially in dense environments. The web has become more sharply defined even as the acceleration of expansion begins to limit its future growth. These maps allow the history of structure to be studied without watching any one region evolve for billions of years. Astronomers compare many regions seen at different ages. Simulations then connect those observations through physical models. A filament in the distant universe is not assumed to become a particular nearby filament. Instead, large populations are compared statistically. This is a restrained kind of time travel. It does not reveal every event. It shows how the balance of environments changes. There are also limits to how much of the web can ever be observed. Light travels at a finite speed, and the universe has a finite age. We see only the region from which light has had time to reach us. Beyond that observable boundary, space may continue, perhaps with more galaxies and more structure, but their signals have not arrived. The observable universe is not the same as the entire universe. It is the part available to us through causal contact. Even within that region, observation becomes more difficult across great distance. Galaxies appear fainter. Their light shifts into longer wavelengths. Small structures become harder to distinguish. Dust, foreground stars, instrumental noise, and incomplete sky coverage all affect the final map. The web we reconstruct is never perfectly complete. It is a model built from limited signals. That incompleteness does not make the structure uncertain in a general sense. The cosmic web appears across many kinds of evidence. Galaxy positions, lensing maps, gas absorption, cluster surveys, and numerical simulations all reveal related forms. What remains incomplete are the details. How does gas enter galaxies along different kinds of filaments? How much ordinary matter is stored in each temperature range? How strongly do filaments influence galaxy spin? Where do the faintest bridges begin and end? How does feedback from stars and black holes alter gas far beyond a galaxy's visible boundary? These questions belong to the next stage of mapping. Future observatories will not replace the web with a simpler picture. They will add layers to it. Wider surveys will measure more galaxies. More sensitive spectrographs will search for thinner gas. Improved lensing studies will refine the distribution of dark matter. X-ray, radio, infrared optical, and microwave observations will continue to overlap. The network will become more detailed because the methods will become more connected. There is a useful parallel in the structure itself. No galaxy explains the web alone. No filament carries the whole pattern. No cluster forms without smaller systems arriving from beyond it. In the same way, no single observation reveals the universe at every scale. Understanding grows by linking measurements, just as matter grows into structure by linking regions through gravity. This connection can remain scientific without becoming abstract. A telescope measures photons. A detector records their energy. Software removes known distortions. Distances are estimated. Motions are compared. A pattern appears only after many concrete steps. The sense of scale comes afterward. You may be resting in a room whose dimensions are familiar enough to cross without thought. Beyond the walls, Earth turns. The solar system moves through the Milky Way. The Milky Way travels with the local group. The group occupies one small portion of the larger web. None of these motions needs to be felt directly to be real. They are shared motions, carried by the structures to which we belong. The cosmic web does not place humanity at a center. It places the Milky Way within a history of matter. The hydrogen in oceans, the oxygen in air, and the carbon inside living cells all became available through processes that unfold inside galaxies. Those galaxies grew because gas entered dark matter halos. The halos developed within filaments. The filaments emerged from early variations in density. The chain does not make human life inevitable. It makes human matter traceable. Atoms do not remember their roots, but physics preserves the sequence. Expansion changed the distances. Gravity gathered material. Stars transformed elements, galaxies exchanged gas, planetary systems formed from what earlier generations of stars returned. The web is the largest visible chapter in that sequence. It is not a final design imposed on the universe. It is the result of simple tendencies acting for immense lengths of time. Matter attracts matter, gas heats and cools, space expands. Dense regions deepen, sparse regions lose material. From these repeated processes, complexity appears. The same network that carries galaxies toward clusters also sets the conditions for isolation. Gravity builds connections locally, while accelerated expansion separates unbound regions globally. The future contains both movements at once. Some structures will draw closer, others will pass beyond reach. The cosmic highways do not lead toward one destination. They record where matter has been able to gather, how it continues to move, and where the growing distance between regions may eventually bring that movement to an end. Before the web becomes too faint for far future observers to reconstruct, its pattern is visible now. Galaxies still mark the filaments. Clusters still gather at the nodes. Light still crosses the spaces between them, carrying the shape of the universe from one region to another. There is no final junction in the cosmic web. Every node belongs to a larger pattern, and every filament fades into another region of structure. A cluster may appear to be a destination because so much matter gathers there, yet even the cluster continues to move. It orbits within a broader gravitational environment, exchanges matter with its surroundings, and remains connected to structures beyond the limits of its own halo. The web has no edge that a traveler could reach. Its boundaries are defined by observation, not by a physical wall. Telescopes see only as far as light has had time to arrive. Beyond that horizon, the universe may continue, carrying more filaments, more voids, and more regions whose light will never become part of our sky. Within the observable universe, the pattern is already enough to fill every scale of thought. A hydrogen atom can spend billions of years moving through intergalactic gas before entering a galaxy. A galaxy can grow inside a filament and then fall into a cluster. A cluster can merge with another cluster, heating gas across millions of light years. At each level, gravity gathers matter without needing a plan. The highways of space are not lines drawn in advance. They are the result of motion. A denser region pulls more strongly. Matter responds. The difference grows. Gas follows dark matter into broad structures, cools in some places, heats in others, and sometimes enters the smaller halos where stars can form. Galaxies carry that history onward, even when their original paths can no longer be reconstructed by the time. Matter reaches a cluster. Much of its journey has been erased by mixing. Gas from many directions shares the same hot atmosphere. Dark matter from smaller halos becomes part of a larger distribution. Galaxies lose some of their individual motion to the common gravitational field. The cluster preserves evidence of arrival, but not a perfect record of every route. The web is both archive and eraser. It keeps the broad pattern while blending the details. This may be why the universe can look ordered from far away and complicated up close. At great distance, filaments curve between bright nodes. At smaller scales, the same region contains irregular groups, disturbed galaxies, uneven gas, shocks, and overlapping motions. The simple shape is real, and so is the disorder inside it. Neither view cancels the other. The web is coherent because gravity acts everywhere. It is complicated because matter has history. Some parts of that history are visible in starlight. Some appear in the bending of background galaxies. Some are carried by X-rays from hot plasma. Some are hidden in narrow absorption lines left by gas too thin to shine on its own. Even emptiness contributes. Voids define the contrast that makes the filaments recognizable. They continue to expand and lose matter, making the crowded regions stand out more clearly over time. Their apparent absence is part of the structure. A map of the universe is therefore a map of both gathering and separation. Matter moves inward toward local concentrations. Large unbound regions move farther apart as space expands. Clusters grow while the distances between distant clusters increase. The web develops while its widest connections become harder to maintain. In the far future, this balance will change what can be known. If accelerated expansion continues, galaxies beyond the local, gravitationally bound region will recede until their light becomes too stretched and faint to observe. The larger cosmic web will gradually disappear from the visible sky of distant future observers. They may see only the merged descendants of nearby galaxies and a dark surrounding space. The evidence available to us now will not always remain available. The microwave background will continue to cool and lengthen in wavelength. Distant galaxies will fade beyond practical detection. The broad expansion history may become difficult to reconstruct from direct observation. Our era is not central in time, but it has access to a wide record. The universe is old enough for galaxies and clusters to have formed, yet young enough for their distant light still to reach us. The web is mature enough to map and still active enough to study as it grows. This does not make the present special in a mystical sense. It makes it observationally fortunate. Light arriving now carries many ages at once. Nearby galaxies show a relatively recent universe. Distant galaxies show earlier stages. The cosmic microwave background reaches us from a time before stars. In one sky, the history of structure is layered by distance. A person beneath that sky cannot see the full web with unaided eyes. The visible stars belong almost entirely to the Milky Way. The nearest large galaxy may appear only as a faint blur under dark conditions. The filaments connecting galaxy groups remain beyond ordinary perception, yet their effects are already present in the motions around us. The Milky Way belongs to the local group. The local group occupies a wider environment shaped by nearby concentrations and under denser regions. Its path is not independent of the network. Our galaxy moves because matter around it is unevenly distributed, just as galaxies across the universe move within their own parts of the web. That motion is not detected as a wind or a steady pressure. The solar system, nearby stars, and surrounding galactic material share much of the same large-scale movement. What can be measured are differences in velocity, changes in position, and the gravitational effects that alter one path relative to another. Scale makes the motion difficult to notice directly. The same is true of cosmic change. Filaments grow too gradually to watch. Clusters assemble across spans far longer than recorded history. Voids widen without any sudden boundary moving through space. The web changes through accumulation. One orbit, one infall, one merger, one stream of gas at a time. There is no moment when the network becomes complete. Gravity continues to reshape the matter it can still reach. Stars continue to form where gas becomes cold and dense enough. Galaxies continue to exchange material with their surroundings. Clusters continue to absorb smaller systems. Elsewhere, expansion carries remote regions farther away. The highways remain active where gravity holds them together, and they thin where expansion wins. This is the final movement of the journey, not toward a destination, but toward a wider understanding of what the routes mean. They are not passages laid through empty space. They are the universe arranging itself. Every filament is a history of attraction. Every void is a history of matter leaving. Every cluster is a history of arrivals. The galaxies are not beads placed on a fixed thread. They formed within the same process that shaped the thread around them. The web and its travelers cannot be separated cleanly. Matter creates the gravitational landscape and then moves through the landscape it has helped create. That feedback has been unfolding since the first small density differences began to grow. It continues in the motion of galaxy groups, in the heating of intergalactic gas, and in the dark halos that guide structures we can barely detect. There is no need to imagine the full network at once. A single idea can remain. Matter does not move through the universe without context. Its path is shaped by what lies nearby, by what formed earlier, and by the expansion of the space in distant regions. From the smallest gas stream to the largest filament, motion belongs to structure, and structure belongs to time. The cosmic web will keep carrying matter long after tonight's light has crossed the room and moved on. The filaments hold their course in the dark,